Assalamu alaikum everyone. Welcome to the course of Real-Time Embedded System. Today we'll continue our chapter number 5 of Wine Wolf's book, and we will discuss program design and analysis. So today is our lecture number 24. Let's start it. So in today's lecture we are going to talk about the compilation flow, basic compilation techniques, and basic program optimizations. So compilation is basically a two-step process. In compilation strategy, we translate and optimize. In other words, we can say that compilation combines translate and optimization. The higher level program is translated to lower level form of instruction. Optimization tries to generate better instructions. So in optimization, we generate better instructions, while in translation, we translate our code from higher level languages, that is C, to lower level languages, for example, assembly. So this diagram basically depicts the basic compilation flow. We start from high level language and we move all the way to assembly language, and through this traversing we go from parsing, symbol table, then followed by machine independent optimization and machine dependent optimization. So it is useful to understand how high level language program is translated. This is translation from top to bottom into instructions. Since implementing an embedded computing system often requires controlling the instruction sequence, so we must need to understand how high-level language program is translated, because implementing an embedded system often requires controlling the instruction sequence used to handle interrupts, placement of data, and instruction in memory. Understanding how compiler works can help you know when you cannot rely on the compiler. For example, if you need to generate something that your compiler is not supporting, so if you understand how compiler works, you can do something at your own. Next, because many applications are performance sensitive, understanding how code is generating can help you meet your performance goals, either by writing a high-level code that gets compiled into instruction, or by writing your own assembly code. So either you can write such a high-level language code that gets compiled into instruction more quickly and easily, because the application you're working on is performance sensitive. We also know that compilation combines translation and optimization. Translation means moving from higher level to lower level, and optimization means trying to generate better instruction. Now, optimization technique focus on one of the program. The optimization technique focus on more of the program to ensure that compilation decisions that appear to be good for one statement are not unnecessarily problematic for the other parts. So if we have optimization, we have optimized the code and we have optimized the code for one statement, it should not be problematic for other parts of the program. Now if you see this diagram, compilation process we have summarized here begins with high level language code. So we have C code here and generally produces assembly code. So we produces assembly code. Now directly producing object code usually duplicates the function of assembler. So we usually don't produce the object code, because if we do so, we are kind of duplicating the assembler, which is very desirable standalone program. And object code is very desirable standalone program. The higher level language program is analyzed here. In this stage, the parsing means analyzed. So we break it down, we analyze into statement and expressions. In addition, symbol table is generated. So once we have the C code, we break it down into statements and expression. and then we generate a symbol table which include the name of the objects in the program. So the symbol table, as we have seen, that it contains labels, so it contains the name of the object in the program. Some compiler may then perform high level optimization. So if after breaking the code and generating the symbol table, some compilers can perform high level optimization that can be viewed as modifying high level input. So what we do in machine independent optimization, we basically modify high level program input rather than instruction. We change or we modify our input. Okay, simplifying arithmetic expression is one of the example of machine independent optimization. So if we have like very complex mathematical arithmetic expressions, if we simplify them, so it is kind of a machine independent optimization. Not all compiler do such optimization. Compiler is a very widely. So we were talking about the simplifying arithmetic expression is one example of machine independent optimization. Not all compilers do such implementation. Compilers vary widely regarding which machine independent optimization they do perform. So it depends like which machine independent instruction we are performing. Either we are like simplifying the arithmetic expression or we are doing something else. So the optimization varies. Whereas in instruction level optimization are aimed at generating code, they work directly on real instruction or on pseudo instruction format that is later mapped into instruction of target CPU. So here in machine dependent optimizations, we basically work on the real instruction rather than on the expressions. We here work on the real instruction or pseudo instructions, and the code here generated here will be mapped into the target CPU. So here we work on the instruction, here we work on the program, and this is how we move from higher level language to assembly language. Let's move on to next slide. So compilation techniques comprises of statement translation. Statement translation, as I've already told you, moving from higher level language to lower level language. Procedure linking is basically depending upon how you are going to call the procedure, how you are going to link it. For example, you might have worked in C, so a procedure has input parameters, it has output parameters, and we need to define the call. Okay, so procedures are just like functions and their linkages, and then we're going to talk about the data structures. So in statement translation, source code, that is your code, is translated into intermediate form such as CDFG. So you convert your statements into control data flow graphs that we have already seen. CDFD is translated into instruction. Then we translate CDFG into instructions. Here's an example of our simple expression from which we have generated DFG. We do not have any control here because we do not have any decision statements, so it is straightforward. We have nodes A, B, then we have operations multiply A multiply B, then we have C minus D multiplying with 5, and ultimately we are getting our result, that is after the summation of these two expressions. So in previous slide we were having an expression, arithmetic expression, and for that we have generated our DFG data flow graph. Now in this, if you see, we have the same data flow graph along with the code. So a code is like breakdown into number of operations that we are performing. That is, first is addition, operator 2 is subtraction, operator 3 is multiplication, and operator 4 is again addition. So this code is written in ARM for ARM processors. So add R4A, it means get address for A. So we are getting the address for A. Move R1 R4, it means that we are loading A. Then ADR R4 comma B, it means get address for B. So we are getting the address and then we are loading. It's the same way as we have loaded A. And then finally what we are doing, we are adding R1 R2 and putting the result in R3. Okay, so what is mean, put W into R3. So this, the result we are going to get is W in R3. Then again we are going to perform operator 2, that's get the address of C, load it, get the address of D, load it, and put X into R6. So we are putting the results in W, X, Y and Z. So here we have the result W, here we have the result X, here we have the result Y, and then finally we have Z. So this is just the data flow graph and the corresponding language in which you are working. So for ARM we are going to use these instructions. So this is how ARM coding works. So if we talk about control code generation, so in control code generation, we have decisions to make. For example, if a plus b is greater than 0, what we are going to do? We're going to set x is equal to 5, else we are going to set 7. Why we are stating this? Because when we have to translate code from higher level language to lower level language, first we need to translate it to control data flow graph, and then from control data flow graph we translate it into instructions. So this is the control code generation. So here we have three operations. Two of them are data flow operation and one of them is control operation. So here's the code of again ARM processor. So this is basically the control code generation. So what we do, we initially get the address of A, we load A with this LDR statement, then we get the address of B, we load B, then we add these A and B and check whether A and B is greater than 0. If A and B is greater than 0, it means that we need to jump. Okay, we need to jump branch less than or equal to. True condition false through branch. Okay, so true case is what we are going to do, we are going to load constant, then we are going to store this value into X, and then we are done with the true case, and then we will come here. Okay, we will come here because we have B statement and done with the statement. Otherwise, if the statement is false, we will not come into the true and we will come here, label 3, we will load constant, get address of X. Here the get of address of X is missing, we will store value into X. So what we are doing, on false we are doing this, on true we are doing this. So this is just the again the recap of control data flow graph, which is the basic block of compilation. So let's move. So after statement translation, which we have seen that we translate our high level code to control data flow graph, the next step for the compiler is procedure linkage. Need code to call and return. We need some piece of code to call and return. We pass parameters. Obviously we need to pass some input parameters, and at outputs we will get some return parameters. Parameters and returns are passed on stack. So in procedure linkage we use stack. Okay, so these parameters and returns are passed on stack. Procedure with few parameters may use register. So if we have few parameters like one or two inputs parameters that we are passing, we can use register. Otherwise, if you have increased number of parameters, we have to use stack. Okay, so procedure stacks are typically built to grow down from higher address. Now we will look into stack pointer and frame pointer. So this is the procedure stack as we were talking about. We have procedure 1. Procedure 1 might have some input parameter. It might have some return, like the way procedure 2 will have some input arguments and it will have some return. And procedure stacks are typically built to grow down, so it is going down. So this arrow, procedure 1, procedure 2, and the next procedure will be downward to procedure 2. So we can see here we have the code. Procedure 1, this parameter is passed int a, and in this procedure we have another procedure, procedure 2, in which we are passing the value 5. So a stack pointer, this stack pointer defines the end of the current frame. So this stack pointer points to the end of the current frame, while frame pointer defines the end of the last procedure. So this is our last procedure. We are currently at this. So this point to the end of the current. This is our current procedure. Procedure 2 is our current procedure. So stack pointer points to the end of the current procedure, whereas frame pointer points to the end of last procedure. Now when a new procedure is called, the stack pointer and frame pointer are modified to push another frame into the stack. So for example, if we have procedure 3 here, what will happen? Our stack pointer will come here and our frame pointer will come here. Okay, so both of them will be modified because initially we have PROC1 procedure 1, so we were here, and inside it is procedure 2. So now our stack pointer is here and frame pointer is here, and these procedure stacks are built to grow downward. And the last thing that is necessary in compilation technique, it is data structures. Different types of data structures use different data layouts. Some address computation of data structure can be done at compile time, other must be done at runtime. So different types, if we have different type of data structure, we have different type of layouts. Address computation of data structure can either be done at compile time or must be done at runtime. So this is the slide explaining the one-dimensional array. C array name points to the zeroth element. So the array name always points to the zero element. So we can see here that's the zeroth element, and C array name points to the zeroth element. And this is one-dimensional array. Okay, drawing in this direction, A0 means first location, A1 second, A2 third. So this is an example of two-dimensional array. You can see that we have array A with rows and columns, row and column. Here rows are same, column are changing. So for many rows, for single row, we will have multiple columns. So that's why we're known as row major layout. This layout is row major. So here if you check, these are M n rows and M columns. So these are M columns. We can transform this two-dimensional array into one-dimensional array with the help of this formula A of I into M plus J, where J starts from 0 to M minus N, and M is basically the number of columns, and I start from 0 to N minus 1. So this is our two-dimensional array. So instruction fields are basically static offsets, means that we can add some fixed value and we get to the next field. So if you see here, structure is comprised of two fields. Number 1 is field 1, number 2 is field 2. So we have two fields. One type is integer, other type is character, and then we have the name of the structure. So this structure name is my struct, and then we have the variable a. So variable a of the type, so this whole name is a, and then we have the type my struct. So what we are doing here, we are putting the address of this structure into this pointer. So this pointer will point towards the first field 1, and then this first field 1 is, we know that, for example, this is 4 byte long. If this is 4 byte long, we can get access to field 2 by adding 4 to this pointer. So this field is 4 byte long. So if we add plus 4 to the pointer APTR, we will get to the field 2. So this way we can say that structures are static offsets.